Imagine for a moment that you are looking up at the night sky. You find that bright, steady point of light, not a star, but a planet. Jupiter. It has been a constant presence for all of human history, a wandering star to the ancients, a swirling marble of cloud to the first astronomers who pointed their telescopes its way. It feels permanent. It feels known. But out there, in the deep quiet of space, something is happening. Something subtle and strange and slowly unfolding. Jupiter is not quite behaving as we thought it would. It holds secrets beneath its famous bands, mysteries in its endless storms, and recent whispers from science suggest we are only just beginning to understand the true nature of this giant world. So let us drift toward it tonight, not with urgency, but with a soft and wondering curiosity. Let us explore what it might mean when we say that something weird is happening to Jupiter. To understand the strange, we must first appreciate the familiar. Jupiter is a world of magnificent scale. It is so large that all the other planets in our solar system could fit inside it with room to spare. It is not a solid world of rock and soil like our own, but a gas giant, a vast sphere of mostly hydrogen and helium with no surface to speak of, only layers of atmosphere growing denser and hotter until they blend into a strange metallic fluid deep within. Its most famous feature is the Great Red Spot, a storm wider than our entire planet that has raged for centuries, perhaps longer. From afar, through telescopes and the lenses of spacecraft, Jupiter presents a face of serene and beautiful turmoil. Swirling bands of cream, ochre, and tan stripe its face, flowing in opposite directions, driven by jet streams that race at hundreds of miles per hour. It is a dynamic world, a churning cauldron of weather, and for a long time we thought we understood its rhythms. We thought its immense distance from the sun, its own internal heat radiating from a slowly shrinking core, and its rapid rotation created a system that was, in its own violent way, predictable. But the closer we look, and the longer we watch, the more we see patterns that puzzle us. The giant is whispering, and we are slowly learning to listen. One of the most profound mysteries of Jupiter has always been what lies beneath those magnificent clouds. The cloud tops we see are just the outermost layer of an atmosphere thousands of miles deep. They are so thick, so dense, and so turbulent that they have acted as a perfect veil. No probe has ever penetrated far enough to tell us what is below. The Galileo spacecraft, when it ended its mission, was sent plunging into Jupiter's atmosphere, and it transmitted data for only about an hour before the immense pressure and heat crushed and vaporized it. It was like throwing a stone into an ocean and trying to understand the seafloor from the briefest splash. So, for centuries, we have been astronomers, peering at the surface of a deep, deep sea, trying to guess the creatures and landscapes that dwell in its abyss. What is the true composition of Jupiter? How much water is hidden down there? How much oxygen? These are not just questions about one planet. They are clues to the very beginning of our entire solar system. Jupiter was likely the first planet to form, and its composition is a frozen recipe from the primordial cloud of gas and dust that gave birth to our sun and all the worlds that orbit it. To understand what Jupiter is made of is to understand our own origins. Recently, Scientists have taken a new approach to this ancient puzzle. Instead of just observing the cloud tops, they have begun to build incredibly detailed digital simulations, combining the physics of fluid motion with the complex chemistry of thousands of reactions. It is like creating a Jupiter in a supercomputer, a virtual world where they can experiment and observe processes that are impossible to see directly. And this new model has revealed something quite significant. It suggests that Jupiter likely holds much more oxygen than we previously suspected. In fact, the estimate is that Jupiter contains about 1.5 times more oxygen than our Sun. This is a key piece of the puzzle. If Jupiter, the solar system's firstborn, has that much oxygen, it changes the story of how the building blocks of planets were distributed in that early cosmic cloud. It hints that the region where Jupiter formed was richer in certain icy materials than we thought. This oxygen is not in the form of the air we breathe, of course. Deep within Jupiter, under crushing pressures, it is bound with hydrogen to form water or mixed into other exotic compounds. This finding helps resolve a long-standing debate and sharpens the picture of our solar system's infancy. But it also highlights a deeper truth. The gases in Jupiter's immense atmosphere move and mix much more slowly than scientists once believed. The churning we see on the surface is just the very top of a profoundly sluggish, deep ocean of gas. Processes that might take years or decades in Earth's atmosphere could take centuries or millennia within Jupiter. It is a world operating on a timescale almost incomprehensible to us, a giant breathing with an unimaginably slow breath. This leads us to the other, more immediate strangeness. While the deep interior may be slow, the upper atmosphere where the clouds live is showing us patterns that defy our expectations in a different way. For 40 years now, we have been studying Jupiter's weather, not just with occasional spacecraft flybys, but with persistent observation from telescopes on Earth and in space. We have compiled a record, a 4-decade-long diary of Jupiter's temperatures and cloud movements. And this long view has revealed something odd. Jupiter experiences what look like hot and cold periods. Its upper atmosphere, in specific bands and at specific latitudes, seems to warm and cool in cycles. On Earth, such cycles are the heartbeat of our seasons, caused by the tilt of our axis as we orbit the Sun. But Jupiter's axis is only tilted by about 3 degrees. It spins almost perfectly upright. It does not have seasons in the way we understand them. There is no planetary reason for its equator to be significantly warmer or cooler than its poles in a cyclical pattern. And yet, the data shows these oscillations happening. It is as if the planet has its own internal rhythmic pulse of heat that has nothing to do with the distant Sun. The changes are not dramatic, not like a switch being flipped, but they are consistent and strange. They suggest that the engine of Jupiter's weather, the transfer of heat from its hot interior out into space, is far more complex and poorly understood than our textbooks suggested. The giant planet seems to be marching to the beat of its own, very slow and very mysterious drum. Think about what this means. Here is a world, the largest in our neighborhood, a fundamental anchor point in our solar system. We have mapped its storms, counted its moons, and sent robotic emissaries to orbit it. And yet, it is telling us that the basic forces that drive its climate are not what we modeled them to be. The planet is not acting quite like a planet should, according to our simpler models. It has its own logic, its own pace, its own hidden mechanisms that we are only beginning to sense. This is the quiet wonder of discovery. It is not about finding answers that fit neatly into boxes. It is about realizing the questions were not even big enough to begin with. Jupiter is reminding us of the humility of science. Every answer unveils a deeper, more intricate question. Consider the great red spot itself. We have watched it shrink and change color over the decades. We have seen smaller storms get swallowed by it, or sometimes crash against its swirling walls and break apart. It is a permanent yet changing feature, an island of fury in a fluid sky. But what fuels it? What keeps a storm alive for hundreds of years? The new understanding of slow atmospheric mixing and internal heat pulses might hold clues. Perhaps the spot is not just a surface weather pattern, but a chimney, a conduit for energy and material from the deep interior, which gives it a longevity no storm on Earth could ever hope to have. Its redness, likely caused by complex chemicals being dredged up from below and cooked by ultraviolet light, is a direct window into processes happening dozens of miles underneath the cloud tops we can see. It is a symbol of the hidden Jupiter, the world beneath the veil. And then there are the colors of Jupiter's bands, those beautiful tawny browns, tans, and whites. They are created by different chemical compounds, ammonia, ammonium hydrosulfide, and traces of water, existing at different altitudes and temperatures. The lighter bands are zones where gas is rising. The darker bands are belts where gas is sinking. This simple up and down motion, driven by Jupiter's fierce rotation, creates the striped pattern. But the new research suggests the chemistry governing these colors is immensely complex. Molecules are not just passively riding the winds. They are condensing into droplets, evaporating back into gas, and undergoing countless chemical reactions as they are transported from the hot, high-pressure depths to the cold, thin upper layers. The beautiful face of Jupiter is a constantly changing chemical painting, its palette determined by processes we are only now learning to simulate. What looks like a simple band of color is the end result of a planetary scale alchemy, a slow distillation happening over epochs. So, when we say something weird is happening on Jupiter, we are not talking about a sudden, alarming change. We are not describing a cataclysm or an imminent transformation. The weirdness is in the subtlety. It is in the slow realization that this familiar giant, this king of planets, operates on principles more nuanced and mysterious than we gave it credit for. Its atmosphere mixes slowly. Its heat pulses in unexplained rhythms. Its composition tells a story of the solar system's birth that we are still deciphering. This is the calm, ongoing weirdness of a universe that is always more intricate than it appears. Jupiter is not breaking the rules. It is showing us that the rule book we wrote was only a first draft, a simplified sketch of a masterpiece. As you lie there, thinking about that distant point of light, you can picture it not as a static picture in a textbook, but as living, breathing entity, a world of unimaginable depth, where storms last for centuries and the air itself moves with the patience of geology, a world where the temperature fluctuates to a rhythm we cannot yet hear, driven by an inner fire and a logic all its own. The sense of wonder comes not from fear of the strange, but from a gentle appreciation of the vast unknown that resides even in our own celestial backyard. Jupiter has been there all along, holding its secrets close, revealing them slowly, one whispered datum at a time, across decades of patient observation. There is a profound peace in this realization. The universe is not a solved puzzle. It is a story that is still being told, and we are here, quiet and small, listening to one chapter of it. The weirdness on Jupiter is a gift. It is a reminder that curiosity is a gentle, endless journey. There will always be another layer to peel back, another question to ask, another mystery waiting in the soft glow of a distant world. So the next time you see Jupiter shining in the night sky, you can know that you are looking at more than a planet. You are looking at a question mark wrapped in clouds, a giant enigma spinning silently in the void, doing things we are just beginning to understand. And there is a deep, quiet comfort in that. The cosmos is alive with slow, majestic change, and our role is simply to watch, to learn, and to wonder. So, let your mind drift with that thought, as softly as a cloud drifting in Jupiter's upper atmosphere. There is no need for conclusions, only contemplation. The giant is there, as it always has been, doing something weird and wonderful, a testament to the infinite complexity of the universe we call home. And that is a thought peaceful enough to drift away on, into quiet and dreamless sleep, under the same sky that holds such gentle, endless mystery. And as we contemplate this slow-motion giant, we can begin to imagine the sensory experience of being there, not as a solid being, for there is no ground to stand on, but as a consciousness drifting through those layers. Imagine descending from the blackness of space, approaching those creamy, swirling cloud tops. The first thing you might sense is the silence, a profound and absolute quiet, for sound needs a medium to travel, and here the medium is so thin and vast that a storm the size of a continent would make no audible roar to an outside observer. But within, if you could listen, the sound would be a deep basso profundo rumble, vibrations felt more than heard, the groan of a world under its own immense weight. You would pass through the high, wispy ammonia cirrus clouds, crystals sparkling in the faint sunlight that is only 1/25th as bright as it is on Earth. The light here is a perpetual soft twilight, tinged with gold and brown. As you drift deeper, the pressure builds, a gentle but insistent embrace that would quickly become crushing. The clouds thicken into bands, great rivers of atmosphere flowing in opposite directions. Here, in the zones and belts, you would be caught in jet streams moving at over 300 miles per hour, yet the scale is so grand that the motion might feel stately, inexorable, like being in the heart of a planetary tide. The colors here are not the vivid hues of enhanced spacecraft images, but more muted, subtle shades of cream, rust, and pale gray, with occasional flashes of deeper ochre where compounds well up from the abyss below. Deeper still, the sunlight fades completely. You are in the eternal night of Jupiter's middle atmosphere. Here, if there were eyes to see, they might perceive the ghostly glow of heat lightning, vast discharges of energy illuminating banks of clouds made not of water, but of ammonium hydrosulfide, giving off a faint sulphurous scent, if such a thing could be smelled. The temperature, curiously, might be quite comfortable here, even room temperature in certain layers, before plunging again and then beginning its final fierce climb into the inferno. This is a realm of perpetual chemical industry. Molecules split and recombine, forming intricate chains, condensing into droplets and vaporizing again, all in a slow, three-dimensional dance dictated by the slow circulation of the deep atmosphere. The new models tell us This dance is far more leisurely than we ever imagined. A parcel of gas, carrying its unique signature of chemicals, might take centuries to complete a single loop from the deep interior to the cloud tops and back again. This is the sluggish heartbeat of Jupiter. And what of that deep interior? As we sink further, pressure turns the gaseous hydrogen into a fluid, and then, thousands of miles down, into a strange metallic liquid. This is not a place of familiar matter. It is an ocean of liquid hydrogen, electrically conductive, swirling around a core that is still a mystery. Perhaps a dense ball of rock and ice, perhaps a diffuse, diluted mixture of elements slowly dissolving into the surrounding metallic sea. The heat here is tremendous, left over from the planet's violent birth, and perhaps from the slow, gravitational squeezing of its own mass. This internal furnace is the ultimate engine for everything above. It is this heat, seeping outward with incredible slowness, that drives the convection, fuels the storms, and creates those mysterious thermal pulses in the upper atmosphere that we detect as warm and cool periods. The planet is radiating more than twice the energy it receives from the sun. It has its own source of warmth, its own inner fire, and the rhythm of that fire's release into the atmosphere is what we are only beginning to perceive as a weird, arrhythmic pulse. This brings us back to the question of why. Why do these thermal cycles exist without seasons? One contemplative possibility lies in the very slowness of the system. Jupiter is not just a ball of gas. It is a fluid planet through and through. The movements within its metallic hydrogen interior, the dynamo that generates its powerful magnetic field, the strongest in the solar system. These processes might have their own long-term cycles. Waves of energy, perhaps akin to the ocean oscillations on Earth, but on a planetary and century-long scale, could slowly propagate upward. They might be influenced by the complex gravitational tugs of Jupiter's many moons, especially the large Galilean ones. Io, Europa, Ganymede, and Callisto constantly stretch and squeeze Jupiter's interior through tidal forces, minutely affecting its fluid dynamics. Over decades, these subtle nudges could manifest as variations in how heat is distributed in the upper layers. It is a symphony of forces: internal heat, deep circulation, magnetic dynamics, and external tides, playing a piece so long that a human lifetime can only hear a few notes. What we call weird is simply our first faint hearing of this symphony. Consider the clouds themselves as characters in this slow drama. The white ammonia clouds are the highest, the cold ones. Below them, in a layer with more pressure and slightly warmer conditions, exist the ammonium hydrosulfide clouds, which give Jupiter its tawny browns and tans. Deeper still, where the pressure is dozens of times that of Earth's surface and the temperature climbs, there should be clouds of water vapor. This water layer is one of the great hidden realms. The new findings about abundant oxygen directly point to a wealth of water hidden in these depths, but accessing it, even with our most advanced simulations, is a challenge. This water cloud layer may be where some of the most significant weather occurs, a realm of droplets and storms entirely hidden from our view, yet its effects ripple upward to shape the patterns we see. A slow upwelling from this hidden ocean of vapor could, over many years, alter the chemistry and temperature of the upper cloud decks, contributing to the cyclical patterns we observe. There is also the fascinating interplay of chemistry and motion. On Earth, Our weather is largely a physical phenomenon. Temperature, pressure, wind. Chemistry plays a secondary role. On Jupiter, they are intimately, fundamentally linked. The colors are chemistry. The storm longevity is chemistry. The very structure of the cloud layers is a chemical stratification. As gases rise from the hot depths, they cool. Different compounds condense out at specific temperatures and pressures, forming clouds at precise altitudes. But the new combined models show this is not a one-way street. These cloud droplets do not just sit there. They fall, they evaporate, they release latent heat, which in turn drives more circulation. They act as tracers, showing the pathways of the deep winds, and they shield the lower atmosphere from our view, creating the veil that has made Jupiter's composition so hard to pin down. The weirdness, then, is partly in realizing that Jupiter's atmosphere is not just a fluid system, but a chemical reactor of unimaginable scale. Its beauty is a direct visual output of its constant, slow, alchemical transformation. As we watch from our distant vantage point, with instruments growing ever more sensitive, we are essentially learning to read this giant's vital signs. The infrared glows that reveal temperature, the subtle changes in cloud color and reflectivity, the slight shifts in wind speed, measured by tracking cloud features over decades. These are Jupiter's pulse, its respiration, its slow blink. And the diagnosis so far is that it is a far more complex and interesting patient than we assumed. It defies simple categorization. It is not merely a failed star, nor is it simply a larger version of the other gas giants. It is its own unique class of world, the archetype of a gas giant. And it is teaching us that the archetype itself is richer and stranger than the definition we wrote for it. This has profound implications beyond Jupiter itself. We have now discovered thousands of planets orbiting other stars. A great many of them are gas giants, some larger than Jupiter, some orbiting perilously close to their suns. We call them hot Jupiters. For a long time, we used our solar system's Jupiter as the model for understanding all such worlds. But if our own Jupiter is more mysterious than we thought, how much more mysterious must those distant cousins be? Our Jupiter, with its complex, slow-moving atmosphere and internal heat cycles, provides a benchmark, but a benchmark that is now shimmering with complexity. It tells us that to understand exoplanets, we must first humble ourselves before the deep, slow mysteries of the one that resides in our own cosmic neighborhood. Every strange datum from Jupiter is a cautionary note, a reminder that the universe rarely simplifies itself for our convenience. So, as you let your mind wander across the gulf of space to that awfully banded sphere, try to feel the scale of time as well as space. Imagine a storm that began before the invention of the telescope, that has persisted through the entire modern age of humanity, and that shows only gradual, gentle change. Imagine you are floating in the deepest, darkest ocean of space. The silence is absolute, a profound quiet that stretches across light years. Around you, stars are not just points of light, but distant suns, each one a silent sentinel to its own private collection of worlds. Most of those worlds are nothing like our own. They are not places of gentle breezes and liquid water. They are monuments to cosmic violence, to physics pushed to its most extreme and unforgiving limits. They are places where the very concepts of day and night, of solid ground and open sky, are twisted into forms of quiet, eternal horror. Tonight, We will drift past a few of them. We will visit some of the most unsettling, the most hostile, the most deeply alien planets ever discovered by human science. This is not a journey of adventure, but of contemplation, a slow, dark look into the abyss and at the strange, terrible beauty that stares back. Our first destination is a world of fire and stone, a place where the sky itself is a crushing incandescent furnace. Its name is Corot 7b. From a distance, it might seem familiar, a rocky world not so different in size from our own Earth. But that familiarity is a cruel illusion. Corot 7b is locked in a deadly embrace with its star. One side of the planet perpetually faces the searing light, while the other is turned forever to the frozen dark. On the day side, the temperature does not merely rise, it soars to heights that defy comprehension. The surface glows with a heat exceeding 2,600 degrees Celsius. At such temperatures, rock does not simply sit there. It melts, it vaporizes. The very ground beneath your feet would turn into a swirling, superheated silicate mist. Now, imagine the weather on such a world. The vaporized rock, these minerals turn to gas, rise into the slightly cooler upper layers of the atmosphere. There, they do something both mundane and utterly terrifying. They condense. Just as water vapor in our sky forms clouds and then rain, on Corot 7b, the silicon and magnesium and iron vapors coalesce. They form clouds of tiny mineral droplets, and then they fall. The sky on the day side of Corot 7b rains pebbles and gravel and stones, a slow, relentless hail of rock, born from the vaporized crust, falling back into the global ocean of lava below. It is a world caught in a perpetual violent cycle of creation and destruction, where the landscape is both liquid and solid, where the atmosphere is made of stone. The night side offers no refuge, only a deep absolute cold nearing 230 degrees below zero, a silent, airless desert locked in permanent shadow. This is not a planet. It is a geological clockwork of pure, elemental fury. We move on, leaving the furnace world behind, drifting further into the void. Our next encounter is not with a planet of fire, but with a world of profound, majestic, and deeply unsettling scale. We approach a gas giant known as J1407b. At first, it seems reminiscent of our own Saturn, a majestic sphere adorned with rings of ice and dust. But as we draw nearer, the sense of scale begins to warp. These are not the delicate, glittering bands we know. The rings of J1407b are a system of cosmic proportions so vast they strain the imagination. They stretch out into space for over 110 million miles. To put that into perspective, that distance is greater than the span between our Earth and our Sun. If Saturn's rings were a bracelet, the rings of J1407b would be a celestial highway encircling a world. This immense structure speaks of a violent and chaotic past. Rings of such scale are not born from gentle processes. They are the graves of moons. The gravitational pull of J1407b, a behemoth potentially dozens of times more massive than Jupiter, is thought to have been so powerful that it reached out and shredded any large satellites that dared to orbit too close. What we see now is the beautiful glittering debris field of that destruction, a monument to celestial violence frozen in silent, graceful orbits. Within these vast rings, there are gaps, dark lanes where the material has been cleared. Some of these gaps may themselves be the signatures of smaller unborn worlds trying to form, or of past collisions so massive they carved canyons through the ice. To drift through this ring system would be to sail through a field of frozen wreckage on a scale that dwarfs entire solar systems, a constant, silent reminder of the crushing power of gravity. Let us shift our gaze now to a world that defies one of our most basic understandings of nature. A planet where logic seems inverted, where fire and ice exist not as opposites, but in a horrifying union. Its name is Gliese 436b. This is a world roughly the size of Neptune, and it orbits so close to its dim red star that its year is just a few Earth days long. The radiation it receives bathes its surface in a heat of nearly 500 degrees Celsius. On any world we know, such heat would mean scorched rock, boiling oceans, an atmosphere of searing vapor. But Gliese 436b is different. Despite the blistering heat, astronomers believe this world is covered in ice. Not the fragile crystalline ice of Earth, but something far stranger and more formidable. This is a substance called Ice X, or perhaps other exotic high-pressure forms of water ice. The secret is not temperature, but pressure. The gravitational force on Gliese 436b is immense, so powerful that it compresses matter into states we can barely conceive. The water vapor in its atmosphere is crushed, forced into a solid state even under the intense stellar heat. The surface, then, might be a landscape of burning ice, ice that does not melt, ice that is hotter than a blazing furnace. If you could stand on it, the very ground would be a solid, searing slab, a paradox made manifest. Furthermore, the star's radiation is slowly stripping away the planet's hydrogen atmosphere, blowing it out into space to form a vast, ghostly tail millions of miles long, like a comet sentenced to eternally circle its own doom. It is a world trapped by its own immense weight, wearing a coat of frozen flame. From the paradox of burning ice, we journey to a world of breathtaking beauty and lethal grace, a sapphire blue marble hanging in the blackness. Do not be fooled by its appearance. This is HD 199733b, and it is perhaps one of the most viciously inhospitable places ever discovered. That deep, captivating azure hue does not come from tranquil oceans, but from a hazy, scorched atmosphere rich in silicate particles. This is a world of endless, violent storm. The temperature here is a constant 1700 degrees Fahrenheit. The atmosphere is not still. It is a screaming maelstrom. Winds race across the planet at speeds that eclipse 5,000 miles per hour. These are not winds as we understand them. They are supersonic tsunamis of superheated gas, moving at 7 times the speed of sound. Within this raging, incandescent atmosphere, those silicate particles are not mere dust. They are the seeds of a terrible precipitation. The heat melts the silicates into droplets of molten glass, and the hurricane-force winds whip these droplets horizontally, sending them slicing through the atmosphere at bullet speeds. It rains sideways on HD 1189733b, a perpetual blistering storm of molten glass shards, scouring the landscape in a deafening, fiery haze. The beautiful blue world is, in truth, a planetary-scale sandblaster, a sphere of endless, abrasive fury, where the very air is a lethal, cutting fluid. We must venture further into realms where planets are not born in the gentle disk around young stars, but forged in the cataclysmic deaths of their suns. These are the so-called zombie worlds, planets that orbit the corpses of stars. Consider a system like PSR B57 plus 12. Here, the central star is no longer a fusion-powered sun, it is a pulsar, the ultra-dense, rapidly spinning remnant of a supernova explosion. This city-sized object contains the mass of our entire sun, spinning hundreds of times per second, emitting beams of deadly radiation that sweep through space like a cosmic lighthouse from hell. And yet, around this stellar corpse, planets have been found. They are worlds that somehow survived the apocalyptic violence of the supernova that created their pulsar master. Or perhaps they formed from the fallback debris of that very explosion. To exist here is to live under a dying sun. The sky would be black, pierced only by the rhythmic, piercing flash of the pulsar's beams, beams of X-rays and gamma rays that would sterilize the surface in an instant. Any atmosphere would have been blasted away eons ago. These planets are likely barren, airless chunks of rock or diamond, bathed in lethal radiation, tidally locked and scorched on one side by the pulsar's energy, frozen on the other. They are monuments to survival in a universe that has already ended, orbiting a ghost. Our journey takes us to even more isolated and desolate realms. Imagine a planet not bound to any star at all, a rogue planet, flung from its native solar system by gravitational chaos, now drifting alone through the interstellar void. These are dark wanderers, and one of the most fascinating candidates is known as CFBDSIR 2149-0403. On such a world, there is no sunrise, no sunset. The sky is a permanent, unbroken tapestry of black, dotted with the faint, unmoving pinpricks of distant galaxies. The only source of heat is the feeble remnant warmth from its own formation, and the slow radioactive decay in its core. The surface would be a landscape of profound cold, approaching absolute zero. Any atmosphere would likely have frozen out, falling as snow of nitrogen, oxygen, or methane, creating a bizarre, frozen wasteland. Yet, in the crushing pressure of a thick hydrogen atmosphere, some of these rogue gas giants might retain a lukewarm interior. But the surface, the boundary with space, is a realm of eternal midnight and deep freeze. The loneliness is absolute. To stand on such a world is to experience the ultimate isolation, a tiny point of matter adrift in an ocean of nothingness, with no star to call home, forever traveling the empty highways between suns. Let us contemplate a world of pressure, so extreme, it transforms the very essence of matter. We arrive at a super-Earth, a planet like 55 Cancri E, a world possibly rich in carbon. Under the immense gravitational force of a world several times more massive than Earth, carbon can be subjected to conditions so severe that chemistry itself bends. The heat is tremendous, thousands of degrees. The pressure, millions of times greater than what we feel at sea level. In such a forge, carbon crystallizes not into graphite, but into its most lustrous and yielding form, diamond. It is theorized that planets like this could have vast strata of diamond within them, not mere veins or deposits, but entire layers, continents worth of crystalline carbon. The core might be a solid mass of diamond. The mantle could be a strange high-pressure fluid or solid carbon mix. The surface, if any solid surface exists under a thick, hot atmosphere, might be littered with diamond mountains glittering under a dim red sun. It is a world of obscene, static wealth, a treasure locked in a vault of impossible pressure and heat, forever out of reach, a beautiful and sterile monument to cosmic alchemy. We turn next to a world that presents a different kind of horror, not of heat or storm, but of a profound and eerie resemblance gone wrong. Kepler 438e was once hailed as one of the most Earth-like exoplanets known, orbiting comfortably within the habitable zone of its star. But its star, a red dwarf, is prone to fits of unimaginable violence. Red dwarfs can unleash superflares, stellar eruptions that dwarf anything our Sun has ever produced. Kepler 438b is bombarded by these superflares with terrifying regularity. Each flare unleashes a torrent of X-ray and ultraviolet radiation powerful enough to strip away not just an atmosphere, but potentially scour the very rock of the surface. Any emerging biosphere would be sterilized again and again. The planet might be Earth-sized, it might have the right temperature for liquid water, but its sky is periodically lit by the flash of a stellar apocalypse, bathing the world in lethal radiation. It is a cruel joke of cosmic real estate, a promising world perpetually poisoned by its own sun, a lesson that habitability requires not just the right place, but also a quiet, stable star. Now, let us venture to the edge of a black hole. While not a planet in the traditional sense, the concept of a world orbiting such an object stretches the imagination to its breaking point. Imagine a planet, or the remnants of one, in a tight orbit around a stellar mass black hole. The sky would be a twisted panorama. Gravitational lensing would warp the light from the background stars into strange, shifting rings and arcs. There would be no primary light source, only this distorted starlight and the utter blackness of the accretion disk, if one exists, a silent whirlpool of doomed matter. The tidal forces would be immense, stretching and compressing the world itself. Time would slow down relative to the rest of the universe. The planet would be locked in a dance with pure gravity, with the point of no return just a momentary misstep away. It would be a world living on borrowed time, in a cemetery of space-time, where the laws of physics as we know them begin to unravel at the horizon. The silence here would be deeper than anywhere else, a silence punctuated only by the imaginary roar of infalling matter and the relentless pull of the infinite dark. Finally, we come to a world that embodies a slow, global extinction event. Venus, our sister planet, is a stark and sobering reminder that hell can exist right next door. While not an exoplanet, it serves as the ultimate prototype for a horrifying planet. A runaway greenhouse effect has transformed Venus into a pressure cooker. The surface temperature is hot enough to melt lead, around 460 degrees Celsius. The atmospheric pressure is 92 times that of Earth's, equivalent to the pressure found a kilometer deep in our oceans. The sky is a perpetual thick blanket of yellow sulfuric acid clouds, and it rains acid, though the droplets evaporate long before they reach the inferno below. The surface is a volcanic plain, crushed under the weight of its own toxic sky. Venus shows us that a planet can take a wrong turn, that conditions can spiral into a permanent global catastrophe. It is a tomb world, a warning written in acid and fire, proving that a planet with similar beginnings to Earth can become a place of utter, relentless hostility. As our journey ends, we are left floating once more in the quiet dark. The horrifying planets we have visited are not monsters. They are simply nature, expressed in its most raw and extreme forms. They are demonstrations of the infinite variety of physical laws, of what happens when heat, pressure, gravity, and chemistry are dialed to values beyond our earthly experience. Their horror is, in a way, a human projection. They are hostile to us, to our fragile, water-based, temperature-sensitive form of life. But in their own right, they are perfect. They are equilibrium states of matter and energy, worlds in balance with their own brutal realities. They remind us of our profound isolation and our incredible luck. Our blue marble, with its gentle temperatures, its protective atmosphere, its liquid water oceans, is the profound outlier. It is the strange world, the rare and quiet sanctuary in a cosmos that is largely vast, cold, violent, and indifferent. The true haunting feeling comes not from the storms of glass or the rains of rock, but from the scale of it all. These terrifying planets are everywhere. For every world like ours, there are likely thousands, millions more like the ones we have seen. They are the norm. We are the exquisite, fragile exception, drifting on a pale blue dot in the immense, silent, and beautifully terrifying cosmic ocean. So, let the silence settle around you once more. Let the darkness be a comfort. And remember, out there in the quiet, the universe continues its work, building wonders and horrors beyond our wildest dreams. The silence that follows this contemplation is not empty. It is filled with the faint imagined echoes of these distant cataclysms, a cosmic background hum of perpetual silent violence. Let us delve deeper into the nature of these alien atmospheres, for they are often the source of a world's particular nightmare. Consider a gas giant not unlike Jupiter, but orbiting perilously close to its star. On such a world, the upper atmosphere is not a placid layer of clouds, but a region being slowly boiled away into space. The stellar wind, a relentless stream of charged particles, acts like a cosmic blowtorch, stripping away the planet's gaseous envelope molecule by molecule. You could witness the slow, astronomical-scale death of a world, a perpetual mist of atmospheric material streaming into the void, forming a tenuous, glowing tail that stretches for millions of miles. The planet is perpetually bleeding its essence into the darkness, a gradual and inescapable dissipation that will continue for eons until perhaps nothing remains but a barren, scorched core. It is a form of violence, not of explosion, but of erosion, operating on a scale and time frame that dwarfs human comprehension, a quiet, relentless leaching of a world's soul. Now, envision a planet trapped in a gravitational dance with not one, but two stars. A circumbinary planet orbits both members of a stellar pair. The sky on such a world would be a source of constant, unsettling change. Two suns of possibly different colors would rise and set in complex, unpredictable patterns, casting ever-shifting double shadows. For parts of its long year, the planet might bask in the light of both stars, suffering under a relentless, double-barreled assault of radiation and heat. Then, as it moves, one star might eclipse the other, plunging regions into a sudden, profound twilight, only for the hidden star to re-emerge with a glaring burst. The gravitational tides from two massive bodies would constantly stress the planet's interior, likely fueling extreme and perpetual volcanism. The very ground would be restless, heated and kneaded by the conflicting pulls of its two suns. The surface could be a cracked and fractured plain, continually spewing forth lava, while the sky above tells a confusing story with its two moving lights. It is a world without constancy, without a single reliable anchor in its heavens, subject to the whims of a complex gravitational melody that permits no peace. There are also worlds where the very concept of a surface becomes ambiguous, a transition not from land to air, but from gas to a strange degenerate matter. Imagine descending into the atmosphere of a super Jupiter, a gas giant dozens of times more massive than our own. The beautiful banded cloud tops would give way to deepening layers of incredible pressure and heat. The colorful ammonia and water clouds would be left far above. As you descend further, the light from the distant star would fade, swallowed by the thick, hot gases. The atmosphere itself would gradually thicken, becoming a soupy, supercritical fluid. There would be no clear boundary, no moment where you land. Instead, the hydrogen and helium around you would simply get denser and hotter until they transition into exotic states like liquid metallic hydrogen, a form of matter that is an electrical conductor, swirling with immense currents. You would be sinking into an endless, dark, electrically charged ocean, where pressures are so great that matter itself is compressed into forms unknown on Earth. It is a world with no bottom, only an infinite crushing descent into a realm where physics becomes strange and forbidding, a perpetual fall into the heart of a perpetual storm. We must also consider the chilling possibility of planets orbiting the remnants of dead solar systems. After a star like our Sun ends its life, swelling into a red giant before shedding its outer layers, it leaves behind a white dwarf, a hot, Earth-sized ember of degenerate matter. Planets that survived the red giant phase would now orbit this dense, fading cinder. The light from a white dwarf is stark and unforgiving, offering little warmth. A planet in the now cold, habitable zone would be a frozen, airless rock, illuminated by the pale, ghostly light of a stellar corpse. Any former atmosphere or oceans would have been boiled away during the star's death throes. The landscape would be one of absolute sterility, a bone-white or charcoal-black terrain under a black sky dominated by a small, intensely bright pinprick. It is a tomb of a world, orbiting a tomb of a sun, a system that has passed through its vibrant life and into a permanent, cold quiet. The horror here is one of absolute finality, a quietus that has already settled in, leaving behind only relics under a dead light. Then there are the worlds sculpted not by the gentle accumulation of dust, but by colossal impacts. Imagine a planet that, in its early history, suffered a collision so titanic that it completely shattered its original form. The debris from this apocalyptic event might have coalesced into a new world, or perhaps a pair of worlds forever bearing the scars of their violent birth. The surface could be a global patchwork of different geological regimes, a chaotic jumble of rock types and minerals fused together in the heat of the impact. The mantle might be uneven, the core misaligned, leading to a magnetic field that is patchy and weak, offering little protection from stellar radiation. The entire planet might still be seismically active, shuddering with the deep tectonic echoes of that ancient, formative violence. It is a world born from catastrophe, its very geology, a chronicle of a single, universe-shattering moment of chaos, a permanent testament to the destructive forces that also build. As we push our imagination to the very limits, we can ponder the theoretical extremes. What of a planet orbiting? Imagine you are floating, weightless, perfectly still. There is no up or down, only a gentle sense of drifting. The familiar sounds of the world have faded away, replaced by a profound and peaceful silence. And before you, suspended in an endless velvet dark, is a single beautiful point of light. Our home, the Earth. From here, it looks like a delicate blue and white marble, wrapped in a shimmering veil of atmosphere. It is both everything we know and just one small world among many. Tonight, let that feeling of quiet wonder carry you. Let your mind drift away from the surface and join me on a slow, gentle journey. We will travel from our warm, familiar sun, past worlds of rock and ice and gas, to the very edges of our celestial neighborhood. This is not a voyage of speed, but of observation, a peaceful tour through our solar system where we can simply look and wonder and rest. So take a deep, slow breath. Feel yourself becoming lighter. The gentle pull of our planet is releasing you. And as you look out into that star-filled darkness, we begin our journey from the very center of it all. Our sun is not just a light in the sky. From here, as we drift closer, it is a presence, a vast, gentle furnace of warmth and light. Its surface is not solid, but a luminous ocean of churning plasma, rising and falling in great slow waves. From this distance, you can feel its energy not as a harsh glare, but as a constant soothing radiance on your skin. It is the heartbeat of our solar system. Every planet, every piece of dust, every comet that graces our night sky, all of them dance to the slow, steady rhythm of this star's gravity. It holds our entire family of worlds in its gentle, unwavering embrace. And as we turn from its comforting glow, we set our course for the first and smallest of the planets that circle it. A world that stays so close to the sun, it feels its warmth more intensely than any other. Mercury emerges from the sun's brilliant halo, not as a world of color, but of shadow and ancient light. It is a gray, cratered sphere that looks much like our own moon. There is a deep silence to this place, a stillness that feels older than time itself. As we drift down towards its surface, we see a landscape sculpted by unimaginable patience. Countless craters, large and small, tell a story of impacts that happened billions of years ago. The ground is covered in a fine gray dust, and without any air to blow it, every footprint, every mark, would remain perfectly preserved for eons. The sky above is a profound and starry black, even in the middle of the day. And there, fixed in that blackness, hangs our sun. It appears enormous here, nearly 3 times the size we see from Earth. But from this silent vantage point, it does not feel threatening. It feels like a watchful, brilliant guardian. The heat on the sunlit side is immense, but here in our imagination, we simply observe it. We notice the long, sharp shadows cast by crater rims, creating patterns of stark light and deep darkness. This is a world of extremes, where the line between day and night is a stark frontier. But for all its harshness, there is a serene beauty in Mercury's simplicity. It is a quiet, rocky testament to the early days of our solar system, a memory held in stone. And as we push gently away from its dusty plains, we look back to see it shrinking once more, a tiny gray pearl orbiting its brilliant star. Our journey continues inward, towards a world that from a distance shines with a soft, creamy light. It is the brightest object in our night sky after the moon, often called our sister planet. But as we approach Venus, we begin to see that this sister world is shrouded in mystery. A thick, unbroken layer of clouds wraps the entire planet, reflecting the sunlight so brilliantly that it gleams like a jewel. There are no surface features visible from here, only a smooth, luminous blanket of white and yellow. This cloud layer is not made of water vapor like Earth's, but of sulfuric acid, creating a permanent global haze. As we descend into this cloud deck, the sunlight begins to diffuse into a dim yellowish glow. The silence is different here. On Mercury, it was the silence of emptiness. Here, it is the silence of profound pressure, of a heavy, still atmosphere. The clouds are thick and soupy, and visibility drops to just a few meters. It feels like floating slowly through a warm, dense fog that has persisted for hundreds of millions of years. The pressure here is crushing, equivalent to being nearly a kilometer underwater on Earth. And the temperature is astonishingly uniform and hot, enough to melt lead. This is a world governed by a runaway greenhouse effect, where the thick atmosphere traps the sun's heat and never lets it go. If we could somehow pass through those endless clouds and see the surface, we would find a landscape of rock baked under an orange sky. Vast plains of volcanic basalt, twisted mountain ranges, and countless volcanoes, some of which may still be active. The ground would glow with a dim, hellish light filtered through the clouds above. But we do not need to go there to appreciate Venus. There is a lesson in its clouds. Venus shows us a possible path a world can take, a reminder of the delicate balance that makes our own blue planet so rare and so precious. As we rise back up through the perpetual cloud layer, breaking into the sunlight once more, we leave Venus behind as that brilliant, unreadable star, a beautiful enigma, forever wrapped in its own veil. And now, we drift back toward the light. Growing larger in our view is the most beautiful sight we have yet encountered, a swirl of blue and white and brown, dotted with green, wrapped in those delicate swirling white clouds. It is Earth. Coming home, even just in passing, fills the mind with a deep and quiet awe. From here, you can see the dynamic nature of our world, the great blue oceans, the brown and green patches of continents, the ever-changing dance of weather systems across the globe. That thin, bright blue line at the edge is our atmosphere. It looks so fragile, so impossibly thin, and yet that tiny shell of air is everything. It is the blanket that keeps us warm, the shield that protects us, the very breath of every living thing we have ever known. We watch as the Terminator line, the boundary between day and night, slowly sweeps across the planet. On the night side, you can see the faint scattered glow of human cities, like tiny embers clinging to the dark. It is a humbling and peaceful sight. Our entire history, every joy and every sorrow, every person who has ever lived, has happened on that one small, beautiful sphere drifting in the vast dark. We linger here for a moment, in silent appreciation, before turning once more to the depths. Moving outward now, we pass the orbit of our home and set our sights on a rusty red dot. Mars has captivated the human imagination for centuries, the planet of war, of mystery, of potential. As we grow closer, its rusty hue becomes clearer, painted across the entire planet by iron oxide, the same compound that gives rust its color. This is a world of gentle deserts. The sky here is not black, but often a pale pink or butterscotch color, filled with fine dust. The air is whisper-thin, barely there at all. The landscape is one of profound stillness. We see the largest volcano in the solar system, Olympus Mons, a shield volcano so wide its base would cover the state of Arizona. It is not a jagged peak, but a gentle, massive slope rising so gradually you might not even realize you are climbing it. Nearby, we find Valles Marineris, a canyon system that dwarfs our own Grand Canyon, a scar across the face of Mars that speaks of ancient geological stresses. If you stood on the surface, the wind would be a faint, almost inaudible sigh, just enough to lift the fine red dust into gentle, slow-moving clouds. The sunlight is weaker here, giving everything a softer, dimmer look. At the poles, great caps of water ice and frozen carbon dioxide, dry ice, expand and contract with the seasons. There is evidence everywhere of a wetter past. Dried-up river channels, lake beds, minerals that only form in water. Mars feels like a world that has gone quiet, a place where great processes have slowed to a near standstill. It is not a dead world, but a sleeping one, holding its secrets in the cold, red dust. There is a profound peace in its barren beauty, a silence that encourages reflection. As we leave Mars behind, its red glow fading against the star field, we are moving now into a new realm. We are about to cross a threshold, leaving behind the small, rocky inner planets and entering the kingdom of the giants. The first sign is not a planet, but a vast, sprawling field of rocky debris. This is the asteroid belt, a region between Mars and Jupiter filled with millions of objects, from dust-sized particles to the dwarf planet Ceres, which is nearly 600 miles across. From within, it is not a dangerous maze as sometimes imagined. The asteroids are so widely spaced that drifting through this region, you would rarely see one. They are lonely mountain ranges floating in space, most of them dark and irregularly shaped, slowly tumbling as they orbit the sun. They are the leftover building materials of the solar system, the pieces that never came together to form a planet. There is a quiet, ancient dignity to them. Each one is a time capsule, a preserved fragment of the solar system's very first days. We pass by them slowly, these silent, rocky sentinels, and as we do, a new presence begins to dominate the sky ahead. It starts as a bright, creamy star, but it grows and grows until it is no longer a point of light, but a vast, striped sphere filling your vision. Jupiter, the king of the planets. It is impossible not to feel a sense of awe. This is a world so large that over 1,000 Earths could fit inside it. It has no solid surface to stand on. Jupiter is a gas giant, a colossal sphere of mostly hydrogen and helium, with a core of perhaps molten rock and metallic hydrogen. What we see is its upper atmosphere, a breathtaking tapestry of swirling clouds. Great bands of white, tan, orange, and brown flow parallel to its equator, moving at different speeds. Within these bands, storms swirl and dance. The Great Red Spot, a storm larger than Earth that has raged for at least hundreds of years, is a deep, rusty oval slowly turning in the southern hemisphere. The clouds themselves move in beautiful, complex patterns, flowing in streams and eddies, rising and sinking in vast, slow motion. As we drift closer, we would be enveloped by the top layers of its atmosphere. The feeling would be of descending into an endless, turbulent sky. The colors would deepen around you. The winds, composed of the same gases that make up stars, would howl with unimaginable force, though from within our peaceful journey we simply observe their power. Lightning flashes, larger than continents, illuminate deep cloud layers. The pressure would increase rapidly, crushing and heating the gases until they behave in strange, fluid, metallic ways. Jupiter is less a planet and more a failed star, a body that gathered immense mass but never quite ignited the fusion fires in its core. It radiates more heat than it receives from the sun, glowing with a gentle internal warmth from its own slow contraction. And around this giant dances a miniature solar system of its own, at least 95 moons. We see the four largest, the Galilean moons, as distinct worlds themselves. Io, a yellow-orange moon dotted with active volcanoes, painting its surface in sulfurous colors. Europa, a smooth white sphere cracked with dark lines, hiding a global ocean of liquid water beneath its icy shell. Ganymede, larger than the planet Mercury, and Callisto, a dark, heavily cratered world. Jupiter is a system unto itself, a complex, dynamic, and majestic center of gravity and motion. Its presence is calming in its sheer scale, and the slow, predictable dance of its storms and moons. We pull away from its immense gravitational embrace, its banded face slowly shrinking, and set a course for the next jewel in the solar system's crown. With its stunning pale yellow hue and magnificent system of rings, Saturn is perhaps the most iconic sight in our celestial neighborhood. As it grows in your view, its beauty is almost dreamlike. The rings, made of countless particles of ice and rock ranging from dust grains to house-sized boulders, catch the sunlight and glow with a soft, ethereal light. They are incredibly thin, only about 30 feet thick in most places, but they stretch over 175,000 miles from end to end. From a distance, they appear as solid, smooth disks, but closer up, you can see they are made of thousands of individual ringlets, like the grooves on a vast cosmic record. There are gaps in the rings, cleared by the gravitational influence of Saturn's many moons. The Cassini division is a prominent dark band, a space of relative emptiness between the brighter rings. The planet itself is another gas giant, similar in composition to Jupiter but with a softer, more pastel appearance. Its cloud bands are subtler, fainter yellows and golds. The winds here are also incredibly fast, but the overall feeling is one of serene grandeur. Saturn is the lightest planet for its size. If you could find an ocean large enough, it would float. And just like Jupiter, it is accompanied by a host of moons. Over 140 of them. Titan is the largest, a world larger than Mercury, shrouded in a thick orange atmosphere of nitrogen and methane. It has rivers and lakes, not of water but of liquid methane and ethane, flowing across a landscape of water ice. Another moon, Enceladus, is a small, bright world of pure ice. From its south pole, geysers erupt, spraying water vapor and ice particles into space, a clear sign of a subsurface ocean. Saturn's system is a place of quiet magic. The silent, graceful arcs of the rings, the soft glow of the planet, the mysterious moons hiding their secrets. It feels like a place from a gentle dream. We drift for a time just outside the rings, watching the play of sunlight on ice before moving on, farther from the sun's warmth than we have ever been. The next world we encounter feels like a shift in the universe's palette. Uranus appears as a smooth, featureless disk of pale cyan, a soft blue-green color. This comes from methane in its upper atmosphere, which absorbs the red light from the sun and reflects the blue and green. Uranus is an ice giant with a composition different from Jupiter and Saturn. It has a small rocky core, surrounded by a deep slushy mantle of water, ammonia, and methane ices, and an outer atmosphere of hydrogen and helium. What makes Uranus truly unique is its tilt. Its axis of rotation is tilted so extremely that it essentially orbits the sun on its side, rolling along like a ball. This means its poles get 42 years of continuous sunlight, followed by 42 years of darkness during its 84-year orbit. As we approach, we look for cloud features, but the atmosphere appears profoundly calm and uniform, a serene, unbroken sea of pale blue. Deeper down, winds do blow, and there may be storms, but from the outside, Uranus presents a face of perfect, tranquil stillness. It has a faint ring system, dark and difficult to see, and a collection of small, dark moons. There is an elegant, quiet mystery to this world. It feels detached, serene, and profoundly cold, drifting on its side in the outer solar system with a dignified silence. Its sibling in the realm of the ice giants is Neptune. As we draw near, the color deepens from Uranus's pale cyan to a rich, deep azure blue. This, too, is from atmospheric methane, but here the color is more intense, a vivid sapphire against the black of space. Unlike the calm face of Uranus, Neptune's atmosphere is dynamic. Even from a distance, you can see great dark storms and bright white clouds of methane ice crystals racing across its face. The most famous of these was the Great Dark Spot, a storm similar to Jupiter's Great Red Spot, though it has since faded. The winds on Neptune are the fastest in the solar system, reaching supersonic speeds, yet from our distant, peaceful vantage, these storms look like slow, graceful swirls in a deep blue painting. Neptune radiates internal heat, like Jupiter and Saturn, causing its weather systems to be active and ever-changing. It has a faint, clumpy ring system and a fascinating moon, Triton. Triton orbits in the opposite direction of Neptune's rotation, suggesting it was a captured object from the distant Kuiper Belt. It is geologically active, with geysers of nitrogen gas erupting from its icy surface. Neptune feels like a world of deep, contemplative beauty. Its intense blue color is soothing, and the slow dance of its high-altitude clouds has a hypnotic, peaceful quality. We are now very far from home. The sun from here is just a very bright star, no longer a disk, but still the brightest point in the sky. Its light is weak, but its gravitational hold remains. Our journey does not end with Neptune. We venture farther into a region of growing darkness and cold. We enter the Kuiper Belt, a vast, disc-shaped region beyond Neptune filled with icy bodies. This is the home of dwarf planets, including Pluto. For a long time, we saw Pluto as just a faint point of light. But as we approach, it resolves into a small, complex world. It has a heart, a vast, bright plain of nitrogen ice shaped like a heart, now officially named Tombaugh Regio. The surface is a patchwork of terrains, dark, cratered regions of methane-stained water ice, bright plains of nitrogen, and mountains of water ice that stand as hard as rock at these temperatures. Pluto has a thin, hazy atmosphere of nitrogen, methane, and carbon monoxide that freezes and falls to the ground as snow when Pluto is farther from the Sun in its long elliptical orbit. It has a large moon, Charon, so big relative to Pluto that they orbit a common point of gravity between them, forever locked in a graceful dance. From the surface of Pluto, the Sun is merely a piercingly bright star in a perpetually black sky. The landscape is frozen in time, a testament to the slow, cold processes of the outer solar system. There is no sound, only an absolute deep freeze silence. Yet in its varied terrain and surprising geology, Pluto feels alive with history. It is a small, distant world that reminds us that wonder exists even in the farthest, coldest reaches. And still, we can drift farther. The Kuiper Belt extends outward, and beyond it lies a theoretical shell of icy objects called the Oort cloud. This is the true frontier of our solar system. From here, the Sun is indistinguishable from the brighter background stars. Its light is a memory. Its gravity is just a faint whisper, still holding comets in orbits that take millions of years to complete. This region is not empty. It is populated by trillions of icy planetesimals, the pristine leftovers from the solar system's formation. Occasionally, the gravity of a passing star nudges one of these ice chunks inward, and it begins a long, slow fall toward the inner solar system, warming as it goes, developing a glorious tail of gas and dust, becoming a comet that graces our skies for a brief, beautiful time. We are at the very edge of the Sun's influence. The space between stars, the interstellar medium, lies ahead. Our solar system, from this perspective, is just a tiny island of light and matter in an unimaginably vast ocean of dark, quiet space. As we begin our long, slow drift back inward, we carry with us the memories of these worlds, the silent, cratered plains of Mercury, the shrouded, mysterious glow of Venus, the vibrant, living blue of Earth, the rusty, quiet deserts of Mars, the majestic banded might of Jupiter, the serene, ringed elegance of Saturn, the tilted, pale blue calm of Uranus, the deep, stormy azure of Neptune, and the small, complex heart of Pluto, out in the frozen dark. Each one is unique. Each one is a world with its own story, its own character, its own place in the gentle gravitational dance orchestrated by our Sun. We are now returning to that pale blue dot, growing larger once more, seeing it from this journey's end, with the experiences of all these other worlds in our mind, makes it seem even more precious, more beautiful, more fragile. It is not just a planet. It is our garden, our cradle, our home in the cosmic dark. The only place we know that has that delicate blanket of air, those vast, life-giving oceans, that vibrant green biosphere. All the wonders we have seen, the gas giants, the ice rings, the distant dwarf planets, none of them have what we have right here. It is a humbling and deeply calming thought. As you feel your mind settling, your breathing slow and steady, hold that image of our solar system in your thoughts, not as a diagram, but as a living, breathing neighborhood, a family of worlds, each on its own path, each turning in its own time, all connected by gravity and sunlight. There is no rush out there. Orbits are measured in years, in decades, in centuries. Storms last for lifetimes. Craters hold their shape for billions of years. It is a realm of immense, patient, peaceful cycles. You are here on this one special world, under the same night sky that has inspired wonder since the first human looked up. The planets you learned about tonight are still there, right now, moving along their silent paths. Jupiter is still turning, its great red spot slowly spinning. Saturn's rings are still catching the sunlight. Neptune's deep blue atmosphere is still swirling with storms you cannot see. And here you are, safe, resting, a part of this same vast, interconnected system. You are made of stardust, riding a pale blue planet around a gentle star in the quiet suburbs of a spiral galaxy. Let that feeling of connection be your anchor, a deep, quiet peace that comes from knowing your place in the cosmos. Not a small place, but a connected one. You are a part of this grand, slow, beautiful story. So, as you drift towards sleep, let your thoughts drift among those quiet worlds. Imagine floating past the rings of Saturn or watching the soft clouds of Jupiter from afar. There is no destination, only the gentle journey. The universe is vast and peaceful and full of quiet wonder. And you, here in your bed on Earth, are a cherished part of it all. Let the silence of space, the slow dance of the planets, and the gentle light of distant stars carry you into a deep, restful, and dream-filled sleep. Good night.
The universe is unimaginably vast. There are hundreds of billions of stars in our galaxy alone, many of which are far older than our sun. It seems highly probable that someone out there must be looking back at us, and yet, no matter how closely we listen or observe, we've heard only silence. This puzzling contradiction is known as the Fermi paradox. It poses a simple yet persistent question. If the cosmos is teeming with opportunities for life, then where is everyone? Consider this. In the grand 4.5 billion year history of the Earth, our civilization is relatively newborn. Meanwhile, the galaxy around us is ancient. If an extraterrestrial civilization had arisen even a few million years before us, a mere blink of cosmic timescales, it could have already spread across many stars. Physicist Enrico Fermi famously pondered this in 1950, asking over lunch, "Where is everybody?" A question that continues to echo in scientific circles. Decades later, we're still searching for an answer. Have advanced extraterrestrials ever existed? And if so, why haven't we encountered them? Over the years, scientists and thinkers have proposed numerous hypotheses to resolve the Fermi paradox. Each offers a perspective on a possible cosmic truth, some hopeful, some grim. Let's explore some of the most fascinating scenarios, traveling through the ideas of danger, isolation, and rarity in search of reasons for the silence of the stars. Our first stop is a place of danger and silence, the dark forest. While this idea originates from science fiction author Liu Xinjin, it resonates as a chillingly plausible reality. Imagine the universe as a vast, ancient forest at night. Each civilization is like a hunter, armed, wary, and moving stealthily among the trees. They know that others might be out there, but revealing their presence by making noise could be deadly. According to the dark forest hypothesis, intelligent civilizations remain silent and hidden out of fear. Any form of life that announces itself risks drawing the attention of another, one that might see it as prey or a threat. In Liu's eerie analogy, the cosmos is filled with silent, paranoid beings, each stalking like a ghost in the darkness. No lights, no signals, only the hush of hunters trying not to be hunted. Why such fear? Because in this dark forest, survival is the only rule. Resources are limited, and any other civilization is an unknown, its intentions and capabilities unclear. Even the weakest seeming culture could suddenly leap ahead with new technology and become a mortal enemy. The safest strategy is to assume the worst If you hear another in the forest, eliminate them before they eliminate you. So everyone stays quiet, erasing any traces of their existence. This hypothesis flips the Fermi paradox on its head. Perhaps the great silence isn't because we're alone, but because the galaxy is full of life forms too terrified to announce their presence. If the dark forest is real, an unsettling thought arises. In searching for friendly extraterrestrials, the simple act of shouting, "We are here," could be the very thing that leads to our doom. However, maybe silence is not just out of fear. It could be the result of something even worse. Not hiding, but extinction. In the cold vacuum of space, another grim possibility lurks. What if we haven't heard from extraterrestrials because they're all gone, perhaps wiped out by an unstoppable threat? This is the berserker hypothesis, perhaps the darkest explanation of all. It suggests that civilizations across the galaxy aren't silent by choice, but forced into silence. The idea gets its name from fictional berserker probes, deadly, self-replicating machines programmed to seek and destroy life. Imagine an automated killer, a robotic virus, spreading from star to star. Such probes, often referred to as von Neumann probes, after the mathematician who theorized self-replicating machines, could multiply exponentially and sweep across the galaxy. If even one advanced species were to unleash something like this out of paranoia or malice, it could mean the doom of all others. Astrophysicist David Brin once remarked, "It need only happen once for the results of this scenario to become the equilibrium conditions in the galaxy." In other words, a single outbreak of berserkers in the distant past could have left the galaxy silent and lifeless. According to this hypothesis, the Great Silence exists because whenever life becomes loud enough to become noticed, say by broadcasting radio signals or launching space missions, berserker probes detect it. Then, like cosmic predators, they descend and erase that life before it can spread. The universe in this grim scenario might be littered with the ruins of civilizations that reached for the stars only to be extinguished. If this is true, we are lucky, or perhaps only lucky for now, that we haven't yet attracted the attention of something predatory lurking out there. Brin once summarized this chilling idea with a warning. If the berserker scenario is correct, we will not find a single intelligent life form out there, including, one day, ourselves. This fear is valid. Our SETI signals, our television broadcasts leaking into space, could one day serve as a beacon leading to our own destruction. And yet, if we're still here, perhaps the worst hasn't happened. Or maybe something or someone is actively protecting emerging civilizations like ours. What if the silence is not enforced by killer machines, but by a form of cosmic caretaking? Let's consider another scenario, slightly less terrifying. What if advanced aliens are indeed aware of us, but prefer to remain hidden, much like zookeepers behind a one-way mirror? This idea is known by the playful name, the space zoo hypothesis. It suggests that we, humans, are essentially an exhibit, or an experiment, being observed by higher civilizations that have agreed not to interfere with our development. In other words, we haven't encountered aliens because we aren't supposed to. In this hypothesis, Earth is akin to a wildlife reserve or a protected island tribe. Think of the uncontacted people of North Sentinel Island in the Bay of Bengal. They live in isolation while the modern world watches from a distance, respecting their wishes and legal protections that ensure that they're left alone. Similarly, advanced aliens might enforce a strict non-intervention policy toward developing civilizations like ours. This could be driven by ethical concerns, like the belief that young species should find their own path without external influence, or simply a form of cosmic anthropology, allowing them to observe us to understand how intelligent life evolves naturally. The zoo or space quarantine analogy implies that evidence of alien existence might surround us, but it is deliberately hidden. We scan the skies and see nothing because we're looking at a one-way mirror. They see us, but we don't see them. This is almost reassuring. Instead of a hostile jungle or an intergalactic slaughterhouse, the universe in this scenario is a vast wildlife park, managed by benevolent or at least indifferent overseers. But there's a catch. It implies the existence of some kind of galactic club with rules we don't know. And this raises another possibility. Perhaps this isn't just passive observation, but active enforcement of cosmic law. If the zoo hypothesis portrays aliens as discrete caretakers, the space police hypothesis depicts them as galactic enforcers. Imagine a highly advanced civilization, or a whole coalition, patrolling the stars and enforcing laws on any rebellious society. As soon as a civilization becomes spacefaring, or starts developing dangerous technologies, the space police arrive and lay down the law. Stay put. These are the rules of the galaxy. This idea is essentially an extension of the zoo concept, but with a more active role. Perhaps an unspoken prime directive exists in space, a term borrowed from Star Trek's non-interference doctrine, and a powerful civilization ensures its enforcement. They might prevent young species from making reckless moves, such as aggressively expanding, sending out self-replicating probes, or developing planet-destroying weapons. In a way, they could regulate behaviors that could threaten others or destabilize cosmic order. If humanity crosses a certain line, say by attempting to create an uncontrollable AI or launching a Van Neumann probe swarm, this hidden authority might intervene, and perhaps not with a friendly warning. Some theorists have joked that the police might simply send an asteroid our way as a harsh lesson. It's a risky test. If we push things too far and nothing happens, maybe there are no vigilant guardians after all. But if they do exist, crossing that line might be the last thing we ever do. So far, there's no evidence that anyone has intervened in our affairs. No alien officers handing out fines for humanity's bad behavior. But there's a certain dramatic appeal to this hypothesis. The idea of an organized galactic community that cares enough to prevent cosmic disasters. If true, perhaps we remain unharmed, not by chance, but by design. Protected until we are mature enough to join the galactic club. But what if, unlike all these scenarios, the simplest answer to where is everybody is there's no one out there, or at least no one capable of saying hello? Perhaps life, especially intelligent life, is exceedingly rare. Earth often seems ordinary, a typical rocky planet orbiting a fairly unremarkable star. But what if Earth is actually the winner of a cosmic lottery? The rare Earth hypothesis argues exactly this, that the emergence of complex life here required such an improbable combination of conditions that it might be practically unique in the universe. In other words, intelligent civilizations might be rare and scattered, or even one of a kind, because the odds were stacked against their evolution. Consider everything that had to happen for us to exist. We are at the perfect distance from the sun, allowing liquid water to persist. Our sun is stable, neither too hot nor too cold. We have a giant guardian, Jupiter, whose gravity deflects comets that might otherwise frequently strike Earth. We have a large moon that stabilizes our planet's tilt and seasons. Plate tectonics regulate our climate, and we've been afforded the exact right amount of time for life to evolve from microbes to multicellular organisms. Even rare events, like ice ages and mass extinctions, might have triggered evolutionary leaps at the right moments. It's a long list of lucky coincidences that, when combined, could be extraordinarily rare. Paleontologist Peter Ward and astronomer Donald Brownlee, who popularized this hypothesis, noted that microbial life might be common. Microbes are hardy and can survive extreme conditions. But the transition to complex animal-like life may require a stroke of luck that happens only rarely. If advanced life needs a planet exactly like Earth, with all these special factors in place, it's no surprise that we don't see alien neighbors. We might literally be the only technological civilization for galaxies around. This scenario is sobering in its own way. The silence around us might not be due to fear, hostility, or regulations. It could simply be that no one else was lucky enough to make it this far. Earth could be a rare oasis in a sterile cosmos. If that's the case, then an immense responsibility falls upon us. In a sense, we carry the torch of consciousness for the entire galaxy. It's a call to cherish and protect the life we have, knowing how fleeting and improbable it may be. And yet even the rare Earth hypothesis doesn't close the case completely. After all, the universe is vast. Even rare events can happen multiple times with enough cosmic dice rolls. Perhaps intelligent life emerges elsewhere, only to encounter obstacles it cannot overcome. And this brings us to a profound concept that looms over any discussion of cosmic loneliness: the Great Filter. The Great Filter is not a single hypothesis, but rather an overarching idea. It suggests that on the path from simple life to an advanced spacefaring civilization, there is a stage that is extremely difficult to overcome, so difficult that almost no one makes it past. The filter might be behind us. Perhaps the leap from non-life to life is so rare that it's only happened once in our galaxy, and we have already passed that threshold. Or the filter might be ahead, an obstacle that nearly all civilizations reach but fail to surpass. If that's the case, we've yet to face the greatest challenge. Economics professor Robin Hanson, who coined the term, described the Great Filter as a probabilistic barrier, a series of highly improbable steps in evolution or development. For example, it may be extraordinarily unlikely for life to evolve from simple single-celled organisms to complex multicellular ones, or for intelligent animals to develop technological civilizations. If even one of these steps is astronomically improbable, it would eliminate the vast majority of life forms before they ever reach the stars. Philosopher Nick Bostrom put it succinctly: if we find the cosmos empty, it might mean almost no one can get all the way to detectable spacefaring status. Something stops them. A chilling implication. If we discover primitive life elsewhere, such as fossilized bacteria on Mars or microbes on Europa, it would suggest that the early stages of life are common. And this would mean the Great Filter is most likely ahead of us. A rare, fatal step may lie somewhere in the future, waiting to be faced. And we must ask, what could this future filter be? Nuclear war? An AI gone rogue? Environmental collapse? One candidate that scientists soberly consider is a pandemic, whether natural or engineered. We've already seen firsthand how quickly a new virus can spread across the world. Even with modern medicine, a pandemic can claim millions of lives and destabilize civilization. Now imagine a disease far more lethal, or a genetically engineered superpathogen. It's not surprising that an advanced society could, either by accident or intent, create something it cannot control. The renowned physicist Stephen Hawking warned that humanity's growing technological power leads to, quote, new ways things can go wrong. And he specifically feared engineered viruses as a potential civilization-ending threat. Could a virus or a plague be the Great Filter that naturally limits intelligent life? Possibly. A sufficiently deadly global pandemic, breaking out before a species can colonize other worlds, could wipe out civilizations or revert it to the Stone Age. Humanity bears the scars of past plagues like the Black Death in the 14th century, which wiped out a third of Europe. One can only imagine alien worlds where successive pandemics destroyed societies before they ever sent a radio signal to the stars. Interestingly, viruses have also been an integral part of evolution itself. Astrobiologists note that viruses are widespread on Earth and may have existed since the origin of life. They drive evolution by forcing organisms to adapt. In fact, some DNA in our own genome comes from ancient viruses. Without this pressure, complex life might never have arisen. In this way, viruses play a dual role. They can accelerate the progress of life, but they can also trigger catastrophic collapse. The idea that a great filter lies ahead is undeniably frightening, but it can also be seen as a call for wisdom. If pandemics, climate collapse, or warfare. And the next great story of civilization will begin. In 1977, humanity embarked on one of its most audacious ventures, launching the Voyager spacecraft into the vastness of space. These twin probes, symbols of our insatiable curiosity, ventured far beyond the familiar planets, aiming to uncover the mysteries of the very edges of our solar system. As we journey with the Voyagers, we bear witness to their incredible odyssey, exploring realms where no probe has ventured before. Their golden records, a testament to the human spirit, carry our greetings to any who might find them in the cosmic ocean. Yet our exploration does not end with the Voyagers. Far beyond the gas giants, in the shadowy fringes of our solar neighborhood, lies Pluto. This distant world, once a planet in our textbooks, now stands as a gateway to the outer solar system. Through the eyes of new horizons, we have glimpsed its wonders, towering ice mountains, vast nitrogen glaciers, and the enigmatic heart-shaped Tombaugh Regio. Pluto, in its silent beauty, challenges our understanding and invites us to delve deeper into the unknown. Beyond Pluto, whispers of an unseen world stir the scientific community. This elusive Planet 9, hidden in the darkness, bends the paths of distant objects with its gravitational embrace. Its existence, inferred from the strange orbits of trans-Neptunian objects, hints at a world yet to be seen, a planet at the very boundaries of our solar system. Join us on a journey to the mysteries on the boundaries of the solar system, where the Voyager saga, the enigmatic Pluto, and the elusive Planet 9 await. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a grand journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which two probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecrafts were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges, budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The imaging science system, a key component of Voyager's arsenal, captured stunning details of the Big Red Spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion the rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras captured the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue dot in Earth-based telescopes. Uranus has presented an enigma to scientists with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle imaging science system camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere. Faint bands of clouds and previously invisible rings girdling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike the Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close. A dynamic and turbulent world, at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune have expanded the frontiers of our knowledge, revealing the diversity and dynamism of the outer planets. These fleeting visits have provided a treasure trove of data that continues to influence our understanding of the icy giants of the solar system. Moving farther and farther away with limited resources, mission controllers face the difficult question of which instruments should be left operational. To extend the life of the mission, non-essential systems, including the camera, were planned to be shut down permanently. But in a moment that epitomized the human spirit of exploration and reflection, astronomer Carl Sagan proposed a bold idea. Before the camera goes silent forever, he suggested that Voyager 1 take one last picture of Earth, a farewell shot of our home planet from the edge of the solar system. On February 13, 1990, the spacecraft warmed up its cameras for 3 hours. The spacecraft's science platform then took a series of images from a distance of about 4 billion miles that would later be combined into a mosaic of the solar system. Among the myriad scientific achievements, it was Voyager 1's gaze toward its home planet that captured the collective imagination of humankind. That pale blue dot is a testament to our insignificance in the vast expanse of space and a poignant reminder of our shared responsibility to preserve and protect the only home we have ever known. In an odyssey that stretches beyond the bounds of human perception, Voyager 1 and Voyager 2 traveled beyond the confines of our solar system, traversing the vast, uncharted territories of interstellar space. This monumental passage marked the first time humanity had traveled beyond the heliopause, the boundary where the sun's influence wanes and the mysteries of the cosmos are fully revealed. The heliopause is the extreme boundary of the solar zone, or domain, where the solar wind, a stream of charged particles emanating from the sun, meets the interstellar medium, the matter that fills the space between the stars in our galaxy. At this boundary, the external pressure of the solar wind is balanced by the internal pressure of interstellar gas and magnetic fields, creating a turbulent region that marks the end of the sun's influence. When Voyager 1 approached this boundary in August 2012, it became the first man-made object to cross interstellar space, providing scientists with direct measurement of the boundary for the first time. At that point, the instruments aboard the spacecraft, though developed in the 1970s, continued to transmit invaluable data back to Earth, recording a sudden decrease in solar wind particles and a corresponding increase in high-energy cosmic rays from outside our solar system, increasingly revealing the history of our universe. Voyager's journey beyond our solar system has not only expanded our understanding of the universe, but it's also paved the way for future endeavors in the never-ending quest to explore space. Their legacy is captured in the vast amount of data about the outer planets, their moons, and the heliosphere, and continues to be a cornerstone for scientific research, influencing the study of fields ranging from planetology to astrophysics. These missions have provided insights into the dynamics of planetary atmospheres, the structure of rings, and the nature of magnetic fields, setting the stage for subsequent missions. In the spirit of Voyager's pioneering voyage, subsequent missions have been designed to delve deeper into the mysteries uncovered by the twin spacecraft. For example, the Cassini-Huygens mission expanded our knowledge of Saturn by deeply analyzing the planet's rings, moons, and atmosphere. Similarly, the Juno mission looked beneath Jupiter's clouds, revealing the secrets of its internal structure and magnetic field. Looking to the future, the scientific community is clamoring for dedicated missions to Uranus and Neptune. These proposed missions are aimed at a comprehensive study of the icy giants, exploring their unique atmospheres, complex ring systems, and diverse moons. Such studies will not only improve our understanding of these enigmatic planets, but will also shed light on the formation and evolution of the solar system. Among the myriad scientific instruments and revolutionary technologies aboard the Voyager spacecraft is a message not for us, but for the unknown, for the future, or perhaps for other space dwellers. That message is the Golden Record, a 12-inch gold-plated copper disc on which are recorded sounds, images, music, and greetings from Earth. The Gold Record serves as a time capsule, a snapshot of humanity and our planet at the end of the 20th century. Its contents have been carefully selected to show the diversity of life and culture on Earth, from the sounds of nature, such as bird song and the sound of the ocean, to music from different cultures and eras, including Bach, Beethoven, and traditional music from around the world. Decisions about the content of the Golden Record were guided by the desire to present a comprehensive picture of Earth and humanity. The team, led by Carl Sagan, put a lot of thought into including content that would not only convey the complexity and beauty of life on Earth, but also reveal fundamental scientific concepts, such as the structure of DNA and the location of our planet in the solar system. The cover of the Golden Record is decorated with symbolic instructions, the universal language of science and mathematics, designed to tell potential aliens how to decipher the disk. These symbols explain the origins of the record and provide instructions on how to play the audio content, ensuring that the message is understood throughout the space, transcending language and cultural barriers. The record is a testament to humanity's hope and desire for contact, communication, and connection, not only with our future generations, but perhaps with other beings who will one day find this bottle tossed into the cosmic ocean, carrying a message of a small, distant world full of life and dreams. As Voyager 1 and Voyager 2 continue their silent odyssey into the depths of interstellar space, the task of keeping in touch with these distant explorers is becoming increasingly difficult. Billions of miles from Earth, the faint signals transmitted by the spacecraft take more than 22 hours to cross the cosmic expanse and come like whispers from the void. The Deep Space Network, an array of giant radio antennas scattered around the globe, serves as the ears of the Earth, listening intently to the faint signals of spacecraft. As the spacecraft travel farther into space, the ingenuity and foresight of the engineers who designed and built these probes becomes increasingly evident. The longevity and success of the missions can be attributed to an amazing feat of engineering. Designed to last only 5 years, the spacecraft have exceeded their expected lifespan many times over, thanks to redundant systems, robust construction, and the use of radioisotope thermoelectric generators, or RTGs, for power generation. These RTGs convert the heat generated by the decay of plutonium-238 into electricity that fuels the spacecraft's instruments and communication systems. As RTG power decreases, mission controllers are faced with making difficult decisions about which instruments should continue to operate. This careful management of dwindling resources ensures that the most important science instruments remain operational for as long as possible, continuing to collect invaluable data at the frontiers of space. Looking ahead, we expect the Voyagers to continue their silent journey long after their last instruments have fallen silent. Driven by the momentum of their initial launch and gravitational support, they'll drift as emissaries of Earth, perhaps for billions of years. The idea that these spacecraft may one day be the only remaining evidence of humanity's existence, taking the golden records into the cosmic ocean, has its poetic note. The final frontier for Voyager is marked not by a physical boundary, but by our ability to communicate across vast cosmic distances. But even as spacecraft fade into silence, their legacy lives on, a testament to human curiosity and the unquenchable desire to explore the unknown. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh Regio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Planitia, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New horizons leap into the unknown, bridge the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty, waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, turning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS. Like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies, each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Archetype, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Archetype, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Archetype, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Archetype's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, that rivaled and even surpassed Pluto in size, sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper Belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or etnos, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, etnos, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP113, and several other etnos, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant, at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of etnos, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, The planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects, coming from regions outside our solar system, could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it.